Walk onto any custom manufacturing floor, and you are immediately surrounded by moving parts. Heavy machinery, raw materials, and specialized operators all have to perfectly synchronize to get a product out the door. If you ask the floor manager how they keep all of that organized on a daily basis, they will usually point you toward a massive, color-coded Excel spreadsheet. They spend hours every single morning dragging and dropping colored boxes, trying to decide which machine should handle which specific job to hit their deadlines. But that manager is fighting an unwinnable war called the job shop scheduling problem. Achieving the absolute perfect order to run a factory is a mathematical impossibility for the human brain. To see why the math breaks down so quickly, look at this animated diagram. It represents a tiny hypothetical factory. You have exactly 10 machines on the left, and you receive 10 custom orders on the right. To find the most efficient schedule, you have to ask, how many different ways can you arrange those tasks? The formula for this is 10 factorial to the power of 10. That results in nearly 40 octillion possible scheduling combinations. To put that volume of data into perspective, if you used a supercomputer to evaluate 1 million schedules every single second, it would still take over 3 million years to find the perfect match. In computer science, a challenge with this specific type of scaling complexity is known as an NP-hard problem. Brute force calculation is physically impossible because there are too many options to check. Because checking every option is impossible, modern industries have had to rely on deeply flawed workarounds just to keep their production lines moving. The human workaround for impossible math is to rely on simple rules of thumb, known as heuristics. A planner will look at the orders and simply say, first in, first out, or prioritize the shortest jobs first. This standard Gantt chart maps a factory schedule using those human heuristics. The colored bars are jobs. The horizontal axis is time. It works, but suffers from one critical failure: these gaping white spaces between tasks. In physical manufacturing, white space is a financial drain. It marks the moments a machine sits idle, burning operating cash while it waits for a part to arrive from another station. Human planners accept this massive financial waste because they lack the raw cognitive power to compress these operations any tighter. To eliminate that white space, engineers realized they had to stop trying to calculate the perfect schedule and start mimicking evolutionary biology instead. They bypass the math entirely by using a framework called a genetic algorithm. Instead of solving the problem, the AI generates 1,000 completely randomized, wildly inefficient schedules, the first generation. Next comes the survival phase. The algorithm instantly deletes the slowest schedules and keeps only those slightly faster than the rest. Then, the AI extracts logic from 2 surviving charts and combines their best traits to breed a superior child schedule. Finally, it introduces a random mutation, swapping individual jobs to ensure the evolutionary process doesn't hit a genetic dead end. The system runs this loop repeatedly. Within 10 seconds, the AI simulates 1,000 generations of this evolutionary cycle, arriving at a mathematically superior schedule without ever attempting to calculate every possibility. This chart is the final product of the algorithm. It is a fully evolved schedule where the idle time has practically vanished, and the tasks are locked together with absolute zero white space. Compare this dense, compressed timeline to the scattered, gap-filled schedule built on human rules of thumb. When you eliminate these idle gaps and pack the timeline this tightly, the same number of machines can often produce 20% more parts in a single shift. This leap in production requires zero new machinery, zero extra floor space, and zero additional labor. It is achieved by letting an AI breed a better week. So genetic algorithms can perfectly orchestrate the heavy machinery, but what about tracking the human workers who operate those machines? For 100 years, the only way to measure worker speed was by having engineers chase employees around the floor with clipboards and stopwatches, a method that is often inaccurate and unpopular. But modern facilities are adopting a new approach. Click the video on your screen to see how computer vision AI is replacing the manual stopwatch by automatically mapping and optimizing human movement down to the millisecond. And I'll see you there.